Farnborough Airfield, the greatest air display in history, proves that Britain now leads the world in aviation. Revolutionary advances, such as the de Havilland Comet, the world's first jet airliner, impress experts from 66 countries. Magnificent indeed is the record of Britain's aviation industry. Overcoming all obstacles, the boys in the drawing offices and the construction shops went all out to put Britain on top. Planes like this Airspeed Ambassador, the Bristol Freighter, Short Seagull, and the Handley Page Hermes have put British aircraft years ahead of any other. The three-rotor Air Horse, making its first public flight, is the world's largest helicopter. It can carry 24 passengers or a 4-ton cargo load. Face to face with such astonishing technical advances, foreign buyers say that in future, civil airlines will rely mainly on British planes. In the military sphere, Vickers Armstrong put on show the Supermarine 510, the newest faster-than-sound fighter. Just off the secret list is the de Havilland Venom, a turbojet fighter. Also newly revealed is this Avro Delta, the paper dart plane. Its new style back-swept wings pierce the sonic barrier with ease. Now showing its paces is the Supermarine 510. The unique Comet, de Havilland's 36-seat jet airliner, is the high spot of the flying display. American orders for this aircraft are already flocking in, and the plane will first go into operation on the New York-Bermuda run. The new Hawker single-seater fighter is next on parade with an amazing demonstration of its almost vertical climbing rate. To end this air show comes the Canberra, the first of Britain's new jet bombers. Powered by Rolls-Royce turbojets, like the majority of the planes on view, the Canberra proves that the jet engine, a British invention, is the aircraft's power unit of today and tomorrow. At Farnborough Airfield in Hampshire, Britain, leading the world in aviation, puts on the biggest air show in history. Ranging from the Neen Viking jet airliner to the short Sealand amphibian, aircraft worth £4 million give buyers from 69 nations an insight into one of Britain's great post-war achievements. The new turn in aircraft design, even to the experienced eyes of Battle of Britain Douglas Bader, seems revolutionary. With the jet engine firmly established as the modern power unit, the familiar air screw seems to have moved to strange positions in a last fight to hold its place. The air world's taxi, the helicopter, is now adapted as an air lorry. The tri-rotor air horse, biggest helicopter in the world, for which a maiden flight is planned next month, carries 24 passengers, or as an alternative, a 3-ton cargo load. In a non-stop flying show, 50 newly designed machines are put through their paces. Foreign visitors are especially impressed by the 40-seater Hermes airliner. Jet engines now power the Tudors, that range of aircraft around which controversy has raged. The Tudor 8, flown here for the first time, is the world's first 4-jet airliner. Jet propulsion opens a wide field for Britain's climbing masters of the air.
Right, stop moving.
Number 35 Bomber Squadron is taking off for the commencement of the afternoon program. R-101, Britain's giant airship, the R-101, is flying over the aerodrome now. She's the largest airship in the world and will fly to Egypt and India in the autumn. The officers from the Central Flying School are now looping in formation. This is an exhibition of aerobatics with the planes leaving a trail of coloured smoke behind them. Gives rather a fine idea of the evolutions that they're performing. Aerobatics. Planes are tied together in threes.
Thousands of air-minded spectators came to Radlett Airfield, Hertfordshire, to visit the biggest aircraft display ever held in Britain. Experts from 50 countries were there too, examining every type of civil and military aircraft, including the transports which played such a great part in combined operations. Thrilling high spots were provided by the latest types of jet plane, giving a display of speed that left the audience gasping. Also in action was the Flying Wing, a revolutionary design linking the present with an exciting future. Still breaking records, the celebrated Lancaster Aries arrives at Sydney on the return from its high-speed dash from England to New Zealand. Carrying out their worldwide experiments in navigation, her crew add fresh laurels to the reputation of those who build and fly our British planes.
Britain's aircraft industry stages the greatest shop window display in history when an impressive 5-day show opens at Farnborough, Hampshire. Thousands of guests from more than 60 countries are thrilled by a brilliant display, and off the secret list is the Flying Triangle, the Avro 707, Britain's latest research jet plane looking like a paper dart. More foreign visitors to the exhibition are astonished at the many advances made in the course of a year. The most interested spectator is Lord Tedder, Marshal of the Royal Air Force. Let's take a glimpse at some of the exhibits in action. Here's the twin-jet medium bomber, the Canberra, particularly imposing by its beauty of line and compelling takeoff. The new Handley Page Hermes. Another addition to this panorama of power in the sky, the Vickers Seagull plane. And now something different, the first public flight of the remarkable 3-rotor helicopter Air Horse. The Meteor 4 fighter, with the most powerful jet engine in the world, can reach 40,000 feet in 5 minutes. Look out as Michael Lithgow, Vickers test pilot, roars past at 650 miles an hour in the Supermarine 510 newest jet fighter. And amongst this whirling galaxy of machines, fast jet planes seem to take pride of place, including the de Havilland Comet 36-seater 4-engine jetliner. One of the latest products of British skill, the Brabazon, overshadows almost everything else, proving without a doubt that Britain now leads the world in every field of aviation.
Bigger crowds than ever flocked to Hendon for the Royal Air Force display, and something like 500,000 people are estimated to have seen it this year, one distinguished visitor being the Duke of Kent. One of the most popular items was the mass parachute leap from plane to ground, and I think I know why it was popular. The pageant was nearly marred by tragedy. Flight Officer V. Hugh Williams crashed in a tutor plane while giving a demonstration of what not to do. The plane was wrecked, but the pilot escaped injury. On view at the display was one of the latest marvels achieved by the Royal Air Force. It was the plane that flies without a pilot, controlled by wireless from the ground.
Right turn.
British aircraft constructors have been showing their latest productions to the world at their 9th annual display at Farnborough, Hampshire. The largest helicopter in the show was the triple-rotor Air Horse, which can carry 4 tons of freight or 24 passengers and is capable of flying the Atlantic. The special front hatch makes for quick loading. Altogether, the hoverplanes were one of the big features of the show, and here's a flight by the world's fastest helicopter, the Fairey Gyrodyne. Overseas buyers were also attracted by the Planet satellite, with its propeller mounted behind the tailplane. With room for 4, the satellite is designed as the family plane of the future. Jet aircraft, of course, were well represented, and this is the Tudor 8, an airliner which leads the world in design. Aerobatics by a jet flying bird fighter put more accent on speed and power. And finally, a flying wing points the way to air developments yet to come. Over to Hatfield, where the de Havilland 108 jet plane supplies a postscript to a story of our progress by flying faster than sound. The first British plane to penetrate the sonic barrier wins fresh honours for its makers and for its pilot, Mr. John Derry.
Farnborough, 1959. The Society of British Aircraft Constructors' 20th Flying Display. With this year's emphasis on Britain's aim to maintain a place in the civil airliner market. These planes, it's hoped, will cut the fares and make flying possible for millions. Military planes, of course, for prestige and spectacle, but for its bread and butter, the industry must now look elsewhere. For instance, to the Vanguard, which Vickers say will halve Europe's airfares. For vertical takeoff, there's still no rival in sight to the Fairy Rotodyne, while the big novelty, fresh from its successful Channel crossing, was the hovercraft. The Argosy, an Airbus for 126, or an air ferry for 6 cars and their passengers. The Vulcan, the latest version, can deliver the standoff bomb, blue steel. And now for missiles. Thunderbird, now in the hands of the Army. It's among 10 all-British missiles on display. And for the first time, the public had a good look at Black Knight. Together with Blue Streak, Black Knight could launch a British satellite. The vast indoor exhibition, ranging from rivets to the latest jet engines. With them, Britain is once again setting new records for aviation exports. Hovercraft of the future may look like this, 400 tonners. And now, the flying. Treble 1 Squadron, the RAF's famous Black Arrows, take off. Formation aerobatics by 16 Hawker Hunters. Dart Herald, to be used by BEA on Scottish routes. The new Comet 4B, bigger and faster than the 4, with no podded wing tanks. The 4B will soon be linking Europe's capitals and flying non-stop to Moscow. With her twin boom, the Argosy can have huge door flaps at both ends. Vanguards have been ordered in quantity. They are scheduled for the Paris route with BEA. And now an aerobatic high spot. Bill Bedford, Hawker's chief test pilot, takes up to Hunter 66A. Along the runway at almost the speed of sound. Streaming smoke, he zooms to 15,000 feet. And then the spin, 13 turns and a 50-second fall. The Blackburn NA-39. This is the Navy's low-level strike aircraft. It goes in at treetop height below the enemy's radar cover. Now it's the Navy's turn. The supersonic scimitars of 807 Squadron. New maneuver, the twinkle roll. Snatching a target from the runway. And how to toss an atom bomb. To demonstrate its possibilities, the Rotodyne carried 30 nurses, a complete field medical company for the British Army. The Bristol 192, in production for the RAF. It can drop supplies, carry 25 troops, or serve as a flying ambulance. For once at Farnborough, it's eyes down instead of up. The 4-ton hovercraft, flying at her officially registered operational ceiling, 13.5 inches above the runway. Is it plane, or bus, or boat? Even the 20 fully armed Royal Marine Commandos leaping aboard don't know. A circus of helicopters, 8 in the air at once, from Westlands and Saunders Row. The Westminster, a flying crane, can lift loads up to 6 tons. And now they all line up to salute the President. Fixed wings again. The Jet Provost, also in production for the RAF, and that's used to introduce pupil pilots to the jet age. Lightnings, all-weather fighters capable of twice the speed of sound. Its wings sweep back 60 degrees. And in the trainer version, pupil and pilot sit side by side. The Vulcan. pompous engines have a total thrust of 70,000 pounds, and with a push like that, the great bomber soars up almost vertically. Treble 1 squadron fill the air again. At times they're only 4 feet apart. They've split into 2 groups of 9 and 7, so there's always something to see. New shape, the windlass loop. Peter Latham, the squadron leader in command, doesn't think this dangerous. He says it needs maximum concentration, so no one's likely to be careless. So, the end of another successful Farnborough, underlining once again the importance of Britain's place in this great industry. Farnborough 1960, and the 21st flying display and exhibition by Britain's aircraft constructors. This year they led the world in vertical takeoff, demonstrated inside by the first glimpse of Bristol Siddeley's swivelling jets, and later outside by the short SC-1, shown here with the shape of the future. Nearly 400 exhibitors with famous names by the score. the Society provides a unique display of aircraft and their equipment, plus the opportunity to examine the vital parts in many of the power plants on show. And now, opening the flying program, 4 Vulcans of Bomber Command's powerful V-Force in a demonstration of their high-speed scramble. All 4 engines of each aircraft are started simultaneously, and well within 2 minutes of the order, all are airborne. Fine weather for another Vulcan takeoff. Coming in at operational altitude, the Prospector 2 demonstrates crop spraying from its 170-gallon tank. The boom-tailed Argosy, already renowned for its versatility, with space for 13 tons of equipment, 69 fully equipped troops, or 89 passengers. Double-ended loading makes for speed and efficiency, an unusual feature being the crocodile jaw opening of the rear door. Now the RAF shows off the Lightning, its first supersonic fighter. With 30 paratroops aboard, the Dart Herald, powered by 2 Rolls-Royce Dart turboprop engines, demonstrates its short takeoff. It's done between markers only 600 yards apart. Westland's Rotary Wing Circus, and this is the first Farnborough to see the whole of Britain's helicopter production in one big group. Now the Victor B-2, biggest aircraft in the show. In service soon, it will carry the standoff bomb Blue Steel. The demonstration Hawker Hunter soars up to 15,000 feet in a high-speed climb. The Vanguard, 425 miles an hour turboprop transport with accommodation for 139 passengers, is the spearhead of the Cheaper Fares campaign. And now the high spot, the short SC-1. This is the world's first public demonstration of combined vertical takeoff and forward flight by a fixed-wing plane. Its 4 lightweight Rolls-Royce engines can lift 8 times their own weight, and there's a 5th for horizontal flight. And finally, Triple One's 18 Hunters. The RAF's Black Arrows, led by squadron leader Peter Latham, have won worldwide fame. But now, these Hunters must give way to Lightnings. So this is their last Farnborough, and these may well be the most polished aerobatics we shall ever see. successful Farnborough has again underlined the importance of aviation of all kinds and of Britain's place in this great industry.
Farnborough 1961 and the 22nd Flying Display and Exhibition of the Society of British Aircraft Constructors, the shop window of Britain's aviation industry. The world's most slender delta, the handy page 115, is the focus of attention in the aircraft park. Renewed acquaintance with an old friend, the twin-seat Hawker Hunter. Striking a colourful note, the Herald, powered by two Dart turboprops. Towering against the Farnborough sky, the Victor's graceful tail dwarfs Scottish aviation's twin Pioneer. In contrast with the modern shapes, the Lincoln icing research aircraft is neighbour to the Jet Provost trainer, and the new 5 to 7-seater twin-engine Beagle. From manned aircraft to the guided weapons park, the Jindivik high-speed target. Blue Steel, the air-to-ground weapon, is demonstrated on its hydraulic loading trolley. The Army shows off its Thunderbirds. And Sea Slug is the Royal Navy's ship-to-air guided weapon. The Bloodhounds nose the sky, and beyond them, Blue Streak reaches for space. Blue Streak, first stage of a satellite launcher. It has an overall length of 60 feet and weighs 90 tons. The two rocket engines are capable of giving a combined thrust of 300,000 pounds. On show in the exhibition, the Stentor rocket motor, which will power Blue Steel, the standoff bomb. The indoor exhibition, with over 300 stands, and all the exhibits receive close examination, whether it's the real thing, such as the Scout helicopter, or a development model of the hovercraft. A rocket motor for vertical takeoff and landing, and the Pegasus ducted fan engine with directionally controllable thrust nozzles. On display are the raw materials of the aircraft engineer, such as stainless and heat-resisting steels. Curiosity and power. A model shape for future transport, the VC-10. Special steels and alloys for very special purposes, such as drop forgings for the most vital components and where strength and reliability and performance are so essential in the modern aircraft engine. Opening the flying display, the two-seat Lightning powered by two Rolls-Royce turbojets with reheat. Capable of supersonic speeds, the Lightning demonstrates its high-G, low-radius turns. The Navy's here, with Sea Vixens and Scimitars. and one vixen can suckle another on the wing at low level. Number 800 Squadron, the Royal Navy aerobatics team of 9 scimitars. Even bad weather doesn't impair their polished performance of formation aerobatics. The helicopters steal more of the limelight year by year. The Army's contribution, 8 skeeters in a barn dance. Fun to watch, but a brilliant display of maneuverability carried out with military precision. The rotodyne, with rototip jets for vertical takeoff and landing, and auto-gyro lift in forward flight. The twin rotor Westland Belvedere looks on as the Whirlwind demonstrates its close support capability. And the Wessex, in service with the Royal Navy, shows ground support with a difference. A long pull and a strong pull with 45 tons in tow. And after a helping hand from Big Brother, the Scout springs away from its mobile platform. One of the most graceful airliners flying today, the Comet. Seating capacity 100 passengers. The Avro 748 takes off on only one of its 2 turboprop engines and is followed by the new Beagle Executive. The Herald 44-passenger transport freighter. And the brilliant little Nat 2-seat trainer with an Orpheus turbojet. The delta wing of the V-Force, the mighty Vulcan. And that was the Argosy, turboprop transport and freighter now in service. Jet Provosts blaze their colorful trail. And the latest Victor. 4 Conway bypass turbojets and a brake parachute in its tail. Following the sky trail blazed over Farnborough by 111's Black Arrows, the aerobatics team from 74 Squadron. 9 Lightnings, Fighter Command's first supersonic all-weather single-seaters. The aircraft's reliability and the pilot's skill combine to give a flawless demonstration of formation aerobatics. And something completely new even for Farnborough, a free drop parachute display by Royal Air Force and Army instructors. Smoke candles trace their fall. And in spite of strong crosswinds, landings are made with precision near the target markets. Another impressive parachute demonstration made by the ground firing of the Martin Baker rocket-assisted ejector seat. And now the handy Page 115, the research aircraft with the improbable shape, a supersonic shape for low-speed research. But there's nothing improbable about the 115's performance as it bridges the gap between supersonic and low-speed handling. Another exciting research project, the short SC-1. 4 jet engines give vertical lift. A 5th engine provides transition to forward flight. Another smooth transition, and the SC-1 makes a controlled vertical descent and landing. And now, Farnborough welcomes speed in the air. And there, in case anyone would care for a ride, goes the latest Hunter 2-seat advanced operational trainer. Once again, the Farnborough Show has demonstrated British design and development in the world on wings. 92 Squadron's Hunters write their brilliant autograph across the sky, symbolizing the collective achievement of a major industry.
Farnborough, 1962, the 23rd flying display and exhibition of the Society of British Aircraft Constructors. Largest aircraft on show, the VC-10, stands aloof. In contrast, the diminutive Beagle-Wallace Autogyro is dwarfed by spectators. With its free turbine engines in repose, the Army Scout helicopter is parked with controls at the ready. For the many interested spectators, there's a close inspection of the Jet Provost trainer, as well as a wide range of other aircraft, such as the Vulcan V bomber. The Trident's low undercarriage attracts attention. In spite of the many applications of jet engines, propellers are still in fashion. The Beagle provides variations on a theme with the Argosy, a versatile freight carrier and passenger transport. The unique rear fuselage doors provide an open reception for curious visitors. From the static park, time now to explore the comforts of aircraft seating. The indoor exhibition, with 350 companies exhibiting, has a record total of 380 stands. Models of current aircraft and ancillary equipment form an interesting display. A section model shows the interior of the hovercraft, which has now become a reality, and for the technician, a wide array of Britain's jet engines to scrutinize. With the accent on vertical takeoff and landing, the Pegasus shows its swiveling thrust nozzles. Wider horizons in engineering development and new shapes mark the advance in aircraft evolution. Opening the flying program, the Navy demonstrates its faultless formations of Sea Vixens and Scimitars. Flight refueling is now a routine maneuver for extending range and endurance. A perfect formation of scimitars executing the twinkle roll. The Buccaneer, a low-level naval strike aircraft designed to operate below radar cover. The superpowered Vulcan is here a flying test bed for a fifth engine, the supersonic Olympus, with reheat installed below the fuselage. Jet Provosts of Central Flying School take off information to demonstrate their skill and aerobatic finesse. Single Lightning demonstrates its high G, low radius turns at low altitude. The world's most slender dozer, the Handley Page 115, investigates low-speed handling characteristics of a wing design suitable for supersonic airliners of the future. Another research aircraft, the supersonic T-188, constructed entirely of stainless steel for flight testing at speeds up to 2,000 miles per hour. The Avro 748 takes off on one engine. And now the helicopter team demonstrates their agility. And the team assemble for a follow-me-leader finale. A man with his head in the clouds and his hands on the Beagle Wallace autogyro controls. demonstrating its stability, a descent with hands and feet off the controls. First of a new breed of aircraft, the P-1127, powered by a vectored-thrust turbofan engine, shows its paces with a neighborly hunter and demonstrates its high rate of climb and maneuverability. Rotatable nozzles on the Pegasus power unit direct the 6.5-ton thrust to the rear for forward flight and downwards for vertical lift. A gentle spot landing makes a fitting climax to this convincing demonstration of the VTOL fighter. Now a new look in civil transport aircraft, the Trident. With 3 Spey bypass jet engines grouped at the rear, it's designed to carry 100 passengers on short trunk route stages up to 1,700 miles. Another new development is the DH-125, a small transport aircraft with twin rear-mounted jet engines. With 4 rear-mounted Conway engines, the VC-10 will carry up to 150 passengers over intercontinental routes at a maximum cruising speed of 600 miles per hour. Shorter landing runs are made possible by the use of thrust reversers on all engines. Now the RAF's contribution, with Lightning's of 74 Squadron turning on the reheat in a mass takeoff. All-weather supersonic fighters weave a high-speed pattern in the Farnborough sky. And now, hunters of 92 Squadron add their skill and precision to a memorable display. Precision flying and faultless performance are synonymous with the Farnborough display, demonstrating the vast potential of the aircraft industry.
Since the days of the Wright brothers, the wind tunnel has been the basic research tool of the aerodynamicist. It enables him to study the airflow over all kinds of aircraft shapes and the magnitude of the aerodynamic forces acting on them. The continuing quest for improved aircraft performance has led to the large and elaborate wind tunnel units of today. These wind tunnels need large-scale powerhouse facilities to provide the very high air speeds at which the aircraft of tomorrow will fly. Elaborate engineering and electronic techniques are used for the precise control of all this power and for recording the performance of the aircraft or missile models being tested in the tunnel. Our aerodynamics department is concerned with the external shape of aeroplanes and missiles. Its aim is to produce a shape which gives the best lifting forces with the least drag, and which has at the same time well-coordinated controls and no undesirable characteristics. By means of accurate scale models in wind tunnels, we can investigate airflow and pressures under controlled conditions at both subsonic and supersonic speeds. The work of our aerodynamicists ranges from theoretical studies of fluid motion to full-scale tests on the complete aircraft. In this tunnel at Bedford, airflow in the region of the leading edge of a delta wing is being studied by blowing smoke over the model. This airflow can be photographed by projecting a narrow light beam across the tunnel. Technicians can also observe the smoke flow through windows in the side of the tunnel working section. In most wind tunnel work, the forces and moments on the model are measured for all flight conditions. Subsonic tunnels, such as this one at Farnborough, have played and will continue to play an important part in the advancement of aeronautical science. In many cases, the detailed pressure distribution over a wing or control surface must be measured. These manometer tubes show the pressures over the surface under test. Since the war, a number of new transonic and supersonic tunnels have been commissioned at Farnborough and Bedford. The 8-foot supersonic tunnel at Bedford can test aircraft and missile models over a wide range of speeds up to nearly 3 times the speed of sound. The model is mounted on a support in the tunnel, and during test, the forces and moments acting on it are measured by electrical resistance strain gauges. Closed-circuit television is used to watch the model sealed from sight inside the tunnel. Masses of data have to be collected, and to save time, results are automatically typed on an electrical typewriter and recorded on punched cards. An automatic plot on graph paper can also be made for detailed analyses. The shock waves present in supersonic flight can be shown by a special technique based on the change in the refractive index of air with change of pressure. In these pictures, the high-pressure regions are shown in black. But we're not always testing at supersonic speeds. Here we're using an airspeed of 30 miles an hour to study the behavior of a dynamic model of an extreme delta shape at high incidence. The results of wind tunnel work are used to verify and extend theoretical work, and the theoretical and experimental aerodynamicists combine in helping to extend our scientific knowledge. During recent years, the extension of wind tunnel techniques to free flight models launched from the ground has played an important part in the work. At ranges at Lark Hill, models are rocket boosted to speed, and during their coasting flight, their performance is recorded by telemetry. Here, the control effectiveness and hinge movements are being measured by deflecting the controls so that the model rolls alternately to port and starboard. Pre-flight models dropped from balloons have also been used to investigate the spinning characteristics of modern aircraft. All the experimental and theoretical work must eventually be digested, analyzed, and made available to the aircraft industry to help foster the development of better aircraft. An important part of the department's work is the assessment of what is technically desirable and possible in the future types in order to choose the most promising lines of research. Eventually, the work culminates in a new aeroplane, and this often comes to RAE Bedford in an early stage of its development. Here, the flying characteristics of advanced types of aircraft are investigated by the Aerodynamics Flight Division. Some of these studies require specially built research aircraft, but appropriately adapted service aircraft are also used. The changing aircraft shapes found beneficial for high speed can also cause some design headaches at the lower speeds needed for takeoff and landing. A camera in the fin of this short SB-5 low-speed research aircraft photographs in flight the smoke from this smoke canister as it flows over the wing. The use of smoke streamers to indicate the patterns of airflow is often a useful aid when interpreting quantitative measurements of aircraft behavior and explaining differences between flight and tunnel results. The smoke flow will also be filmed by an observer flying in an accompanying aircraft. In this case, as in many others, the observer is one of the technicians working on the test program. The smoke is discharged from a pipe just ahead of the leading edge and shows how, on a highly swept wing at incidence, the mainstream flow may leave the upper surface near the leading edge and reattach further back on the wing, the airspace underneath being occupied by a tightly rolled vortex. Using different positions for the smoke pipe, the flow over the whole wing can be mapped over the speed range. To reduce the compromise needed for good low-speed and supersonic flight, it may be desirable to use direct jet thrust to achieve vertical takeoff and landing. The Rolls-Royce Flying Bedstead is a research vehicle on which the Flight Division has been conducting experiments in the unusual stability and control problems associated with this new technique. The jets of the two engines eject downwards, and the pilot's controls are connected through electronic stabilizing circuits to 4 compressed air nozzles mounted on outriggers. The next stage of development is the short SC-1 aircraft, which will convert to normal winged flight after vertical takeoff. The dynamic behavior of an aircraft is perhaps the most prolific field of full-scale research and requires the use of specially designed high-precision instrumentation. Each instrument must be fully calibrated in the laboratory before being fitted in the research aircraft. The instrument's response must be checked at various oscillation frequencies if accurate results are to be achieved. The accelerometer under test on this table will measure the acceleration or deceleration of the aircraft along one of its 3 axes. A mass suspended on spring supports, when displaced under acceleration forces, moves a wiper over a potentiometer. The resultant signal operates a mirror galvanometer, one of several mounted in a recorder carried in the aircraft. The light beams from each of these galvanometers leave a series of traces on a strip of photographic paper moving behind a slit. Another type of instrument frequently used is a small spring-restrained gyroscope to measure the rate of rotation of the aircraft about one of its 3 axes. Some installations, however, require extensive calibration in the aircraft itself. An example of this is the measurement of tailplane loads on a Hunter in maneuvers. Appropriate parts of the tail structure have been fitted with electrical resistance strain gauges, and forces representative of flight conditions are applied to the tailplane by suitable loading gear in the hangar. At each condition, a record is taken using the galvanometers and recorder which will be used in flight. The flight tests are carried out by service test pilots attached to the establishment who work in close cooperation with our scientists. In addition to their piloting skill, they need a special understanding of research work so that they can obtain the maximum amount of useful data from their flights. In addition to the various instruments in the aircraft recording its motion, a cine camera in the fin can film wool tufts which are sometimes attached to the wing. These tufts can show the rapid changes in the airflow over the wing during maneuvers. This flight is to investigate the detailed behavior of the Bolt and Paul delta in rapid rolls. As a further aid to interpretation, the rolls are filmed from an accompanying aircraft, and like so much research film, it gets honorable scars and scratches by constant viewing to obtain data. During the rapid roll on this aircraft, inertia forces cause an increase of incidents which the pilot has to oppose. The oscillation of the tufts near the wingtip show a flow breakaway or partial stall during the roll due to this effect. After the flight, the records are processed and the critical portions are selected for detail analysis. The changing positions of the continuous traces are measured off, and corrections are applied for the characteristics of the instruments as previously determined in the laboratory. After further computations, the results are plotted and compared with other data, and the program for the later flights can then be decided. These continuing additions to our knowledge of high-speed flight enable our researches to be extended still further into the supersonic speed range. The information and experience gained in this way provides an essential background for the design and safe development of more efficient aircraft of all shapes and sizes for both civil and military purposes. The development of rocket motors and ram jets, of modern radar and electronic guidance systems, and the mastery of supersonic flight have opened up wide new possibilities in the military and scientific use of guided missiles. Few recent developments call for research in such a wide variety of fields. In our guided weapons department, physicists, aerodynamicists, mathematicians, and electrical and mechanical engineers work side by side on a wide variety of problems, ranging from supersonic aerodynamics to the engineering and manufacture of precision components. Theoretical and laboratory work is centered mainly at Farnborough, while rocket motor research is done at RAE Westcott near Aylesbury. There are many problems to solve before an experimental missile, known as a test vehicle, can be assembled and sent for firing on the guided weapons ranges at Aberporth in Wales or at Larkhill on Salisbury Plain. Some missiles are tested on the ranges at Woomera in Australia. New kinds of missile mean new techniques of control and guidance, new problems for the aerodynamicist and the propulsion engineer, and new shapes in the air. But flight trials are expensive and take a long time. They are normally only undertaken for proving systems or to obtain data that cannot be derived by other means. Much cost and effort is saved by investigating the behavior of a simulated model of the missile in an electronic computer. At Farnborough, TRIDAC, one of the largest analog computers in the world, is being used for this purpose. Once the complicated program for the machine has been agreed, TRIDAC makes possible the study of complete weapon systems, and gives designers a preview of the results that can be expected in practice. Units are interconnected through plug leads to build up an electronic model of the system being studied. Guidance information is routed to the control system, and gyro signals are linked to the simulated fins. Power for a machine of this size is considerable, and the 650 kilowatts required is supplied by a special substation. Voltages must be accurately stabilized, and an elaborate monitoring system is provided to indicate any malfunctioning. Hydraulic servo mechanisms enable TRIDAC to compute the position and attitude of the missile in three-dimensional space and make possible measurements of the final accuracies to be expected from the weapon system being simulated. Precision resolvers constantly compute the necessary functions of the angles of pitch, roll and yaw as the missile maneuvers. The raw data from the wind tunnel, the paper studies of the control engineer and the radar guidance signals combine to tell the story of the combat between a theoretical bomber and a hypothetical missile. The motions of target and missile are displayed on plotting tables, one pen representing the target aeroplane and the other the missile attacking it. Relative motions are plotted and accuracy assessed. The effects of height and speed, of target maneuver and wind are watched, noted and compared, while from many channels records of forces, moments, rates and angles flow to swell the sum of knowledge and speed the development of a new weapon. But before we go to see how a new weapon is prepared and fired on one of our test ranges, let's go to our rocket propulsion department at Westcott in Buckinghamshire and see how research on the rocket engines for these weapons is carried out. These general views of the department clearly show that the test sites, laboratories and offices are dispersed over a wide area, an essential requirement arising from the nature of the work. The development of rocket engines creates its own peculiar problems and demands the work of chemists and physicists, metallurgists, mathematicians, designers and engineers, all of whom require up-to-date equipment for their investigations. These pictures show examples of apparatus used for the testing of materials. Here a sample of gas is in the process of being analyzed using a mass spectrometer. The study of combustion phenomena at low pressure is yet another aspect of the work. These studies are examples of the basic work at RAE Westcott, which is necessary if developments are to proceed on sound lines. To be effective, scientists and engineers require the support of designers and skilled craftsmen. The incessant demand for improvements in the performance of rocket engines gives the incentive for evolving new designs and manufacturing techniques. No rocket engine can outmatch its weakest component. Facilities have therefore been installed for testing the individual components before final assembly into the rocket engine. This sequence shows just one aspect in the testing of a propellant injector plate. The solid propellant rocket motor and the liquid propellant rocket engine are the two basic types of rocket propulsion units. The solid motor has its propellant stored within its combustion chamber and has no mechanical moving parts. The liquid propellant type is more complicated mechanically. All rocket propellants are potentially explosive, and these pictures indicate not only the varied type of the test sites, but the care that has been taken in their construction to comply with strict safety precautions to ensure that engineers and scientists are protected during tests. The successful firing of an engine is the only proof that its design is satisfactory. Except in special cases, direct observation is not permitted, and viewing is normally carried out with the aid of a special periscope or other means. The condition of the unit after firing is not sufficient to judge whether it was satisfactory. A complete knowledge of the behavior throughout the firing is essential, and this can be obtained only by equipment operated electronically. Much of the special measuring equipment has been developed at RAE Westcott, but standard recording instruments are used whenever possible. Now let's go and see the firing of a complete weapon at the Aberporth test range. RAE Aberporth on the Welsh coast in Cardigan Bay is one of the rocket ranges controlled by our trials department. Many of the rockets launched here are fired as part of research and development programs. Typical of these is this rocket, or test vehicle as it is known, which has been brought to Aberporth by road and is being wheeled into a preparation room for pre-flight checking. The internal equipments are systematically tested. All mechanical and electrical functions are checked and final adjustments are made. When all these tests have been satisfactorily completed, the rocket is taken from the preparation room to the launching apron. On the launcher, further checks are made in conjunction with the range instrumentation. Hydraulic fluid is pumped in for operating the controls. Operators in protective clothing then fill the tanks with fuel for the rocket motor. Meanwhile, the range instrumentation is given a final check. Tracking radar is adjusted. Telemetry equipment records radio signals from the rocket which give information about the behavior of components and the conditions within the rocket. Doppler equipment records the speed by radio methods. Kinetheodolites follow the rocket's flight and give a film record of bearing and elevation angles. High-speed cine cameras give a pictorial record in slow motion of the behavior of the rocket during flight. The operations room staff have been following the rocket's progress since it arrived in the preparation room. When it is ready, the launching area is cleared, firing circuits are checked, and the sequence of firing instructions begin. The rocket is fired, its flight being followed and recorded by the ground instrumentation. In this trial, the guidance system is being tested against a spherical target suspended from a balloon. In further trials, the rocket is fired against a target aircraft. Here the rocket passes the target well within lethal range. Structural research, development and testing is essential to ensure that aircraft and missiles are safe and at the same time efficient. Constant vigilance is necessary to make sure that the lightest possible structure is used that possesses adequate strength and stiffness throughout its operational life. In the past decade, considerable emphasis has been placed on the fatigue problems of transport and operational aircraft. The necessary information on the loading actions subjecting the structure to fatigue is obtained from a variety of sources. Here is one of them, the special test frame in which our structures department can carry out full-scale fatigue tests on complete aircraft. Another important development has been that of instruments recording the accelerations imposed on the aircraft structure by maneuvers and flight through atmospheric turbulence. Experiments on components such as sheet specimens and joints provide an essential background. This slow-motion picture shows the fatigue failure of a sheet specimen in one of our test rigs. In the case of aircraft with a pressure cabin, a special problem arises because failure of the cabin under representative air pressure would result in a major explosion. These comparative test specimens show how we solved the problem by testing in water and illustrates how this helps to localize the damage when failure occurs. By using a special water tank, we can apply this principle to pressure cabin fatigue test on an actual aircraft. The fuselage is placed in the tank with water inside and outside the cabin. The aircraft wings project through rubber sealing glands in the sides of the water tank so that the wings can be flexed to simulate the gust loads encountered in flight. At the same time, the water pressure inside the cabin is increased to simulate the appropriate air pressure of high-altitude flight. The loading conditions of flight are imposed by the strength testing technique of hydraulic jacks at appropriate parts of the structure. Problems involving the stiffness of the structure are many, but there is no doubt that the dominant one is that of flutter. This rocket-propelled aircraft model shows how the interaction of the aerodynamic, elastic and inertia forces can lead to catastrophic failure in a few seconds. All practical, theoretical and experimental techniques are used in the attack on this problem. Using this Lancaster aircraft as a flying guinea pig, we have fitted it with an electrodynamic vibrator, which excites a torsional mode of vibration on the fuselage. The wind tunnel model provides considerable data on both the aerodynamic forces and on flutter, but has the obvious limitation of damage to the tunnel following a flutter failure. The use of rocket-launched models overcomes this difficulty. A further limitation applicable to most structural fields is that it is generally impracticable to make realistic models of specific projects, and this underlines the need for experiments and tests on the complete structure. Prior to first flight, a complete picture is obtained of the dynamic characteristics of the aircraft by means of the ground resonance test, in which the aircraft is suitably supported and vibrated through a wide frequency range. In flight, the margin of safety is determined by subjecting the structure to defined impulses and checking that all modes of vibration are adequately damped. Small explosive charges, called bonkers, fitted above and below the wings, can be used to give the impulse during flight. Here is a further test, filmed in slow motion. The motion was slowed up by a factor of 5. Aircraft and missiles flying at supersonic speeds are subjected to aerodynamic heating caused by compressibility and skin friction. This rocket model flying at a speed of Mach 5 shows what can happen. The fins break off due to kinetic heating. Here we reproduce in the laboratory a similar heating effect on a metal specimen. This heating has two major effects on the structure. Firstly, the transient stresses arising in the heating period during acceleration or the cooling period during deceleration, and secondly, the temperature effects on the material properties during the saturated state after prolonged steady flight. Experimental techniques are therefore required to represent the kinetic heating in laboratory tests of components and complete structures in conjunction with representation of air and inertia loadings. A practical technique for most applications is of infrared lamps for the heating elements with an appropriate computer-controlled system varying the voltage to the lamps. The heating intensity varies significantly over the surface of the structure. It is therefore essential to have a large number of individual heating elements, each with its own computer-controlled channel. This model demonstrates how we apply the technique to heat testing a full-scale wing. The case of the re-entry of a ballistic missile into the denser atmosphere at low altitudes requires representation of very high kinetic heating rates, well beyond that obtainable at present by infrared lamps. This test rig, one of several used for the investigation into Britannia engine icing, shows how our mechanical engineering department does research into the climatic engineering problems which occur at times when new types of military and civil aircraft experience unusual icing difficulties. The quarter section of a Britannia engine nacelle was fitted in the rig and the icing conditions encountered in flight were simulated. The ice for the tests was manufactured in one of our cold chambers. After powdering, the ice was graded to the correct particle size for blowing into the engine. During a test, the pressure, temperature and velocity of the air feeding to the engine was carefully adjusted to represent flying conditions at altitude. Water and ice could also be fed into the air supply. When ice was fed in at a controlled rate, the build-up of ice in the engine intake was observed through various observation panels. This Perspex model of part of the Britannia engine air intake shows how the ice first builds up and is then sucked into the engine compressor in lumps large enough at times to upset the engine airflow and cause interrupted combustion. Now let's see how the ice builds up inside the actual engine nacelle. By studying the positions in which the ice forms and the way in which it first builds up and then breaks away again, both in this and other test rigs, it was possible to develop methods of overcoming the trouble. One of these methods was to use air jets to blow the ice away, as shown by these cleared passages. So far, we have been telling you about aircraft and their equipments, but what about the safety and comfort of the men who fly them? Aircrew must be protected from the effects of reduced pressure, extremes of temperature, rapid accelerations, noise and glare when flying such machines as this, the Javelin. The pressurized cabin affords certain protection, but if this should be damaged by enemy action, emergency protection must be given by special clothing. This must be as carefully engineered as the aircraft. Our mechanical engineering department is responsible, amongst other things, for some aspects of this special protective clothing and equipment. The pressure breathing jerkin, which this pilot is wearing, is designed to provide counter-pressure to the trunk, and in conjunction with the pressure headpiece and special oxygen regulator, gives short-term protection against anoxia at altitudes greater than 40,000 feet. Aircrew are cooled in the tropics or during low-level high-speed flight by evaporation of their sweat. The man in white is wearing an air-ventilated suit, which distributes up to 1 pound of air per minute over the body through 144 jets to ensure uniform and efficient cooling. Fleet Air Arm aircrew, like the man on the left, are equipped with immersion suits. The fabric of this garment allows free passage to water vapor when dry, but when immersed in water, the fabric fibers immediately swell and untwist to close the pores of the material, keeping the immersed man dry. A full pressure suit is required to provide long-term protection from bends and anoxia at high altitudes. At differential pressures up to 5 pounds per square inch, the garment must remain sufficiently flexible to allow aircrew to perform their flight duties. Flying suits, uniforms and even underwear must be specially tailored to ensure compatibility between garments, pipes and connections. Garments must be designed so that they do not impede movements or cause discomfort. Note the cut of this anti-G suit. The design of man-carrying parachutes for aircrew, paratroop and other requirements is another aspect of our work constantly under review. Here a group of paratroopers are jumping from a Hastings aircraft. A man weighs around 200 pounds. But when it comes to supply dropping equipment for the Army, we have to think in terms of tons. This demonstration, filmed in slow motion, shows how we deliver a 1-ton truck from the air. The cluster of small parachutes first pulls the load out of the aircraft and then opens the main parachute cluster. And this is what it's like at the receiving end when a Bren gun and carrier lands. Here is another application of the parachute, to shorten the landing run of large aircraft. In this case, the Vulcan is at the end of its run, and we can see the ribbon parachute in detail. The lower part of the canopy is fluttering in the jet stream. Here is something faster, the Fairy Delta with a cluster of 3 brake parachutes. The design of ejection seats for the emergency escape of aircrew from high-speed aircraft presents a number of problems. Under high-speed conditions, it is impossible for aircrew to get out of their aircraft, so provision is made for ejecting them in their seats. In this test, made during flight, a dummy man was used. Sometimes it's not possible to remove the cockpit canopy, and escapes have been made through the perspex hood. That slow-motion shot of a ground test using a dummy man shows what happens. We use this ejection seat test rig to help us with our researches, and as you can see, the ride is, to say the least, exciting. When ejection is not possible and the pilot makes a crash landing, the aircrew's safety harness and seats must be capable of standing up to severe loads. They are tested on this rocket trolley, which can be stopped from 75 miles an hour in 6 feet. It also shows what happens if the harness fails. Investigations are also made into high-altitude aircraft fires. A bomb-shaped target was released from an aircraft to determine the maximum height at which aircraft fuel can be ignited by incendiary ammunition. The target bomb measures 16 feet long by 32 inches in diameter. Inside is fitted a telemetry transmitter and a fuel tank. During a test, the transmitter sends out signals from heat recorders surrounding the fuel tank. A gun was fitted in the tail of the bomb. At a known height, a delay device on the bomb nose fired the gun and projected an incendiary shell into the fuel tank. The telemetry set transmitted the results of the test to a ground receiving station for analysis. However, fires are not always catastrophic. These flames from FIDO, the fog dispersal aid we helped to develop during the war, have their continuing applications for both the military and civil flying of today. organization like the Royal Aircraft Establishment must have the tools for turning ideas into actualities, and pretty elaborate tools they have to be to tackle some of the intricate things we have to make. But simple or intricate, before the workshop wheels can start turning to make a part or a complete experimental equipment, it has to be designed. This important aspect of our work is dealt with not only by our main design office, but by the 25 or so design offices attached to most of our departments, each one staffed by designers who have made a special study of their department's requirements. The many workshops required to cope with all this work are equipped to carry out a wide variety of operations, varying from heavy fabrication jobs to work calling for the highest degree of precision, like the making of intricate guidance systems for missile or supersonic aircraft models. Apart from the main workshops, most of our departments have their own model shops where equipments can be made up under the direct supervision of the scientists and technicians working on a particular project. We even have our own foundry. Here we are casting the metal wings for an aircraft model which will be rocket-propelled to fly at a speed of Mach 2. There's no time in this film to tell you about all those who, by their combined services and skills, help to keep the research wheel turning and our research aircraft flying. No small job this, considering the number of research aircraft of all types in our care. Many of them are of advanced design and all carry intricate test equipments. There are many jobs to be done, and each in its way calls for special training and the high degree of skill which the Royal Aircraft Establishment has made special efforts to maintain. Our technical college, which carries out instruction over a wide range of subjects, makes an important contribution to this field. Its work includes courses for all types of apprentice, leading to engineering degree, national certificate, and city and guilds qualifications, together with courses for many other specialist requirements. The laboratories are equipped with up-to-date apparatus for experiments in the wide range of the technologies studied. The student is thus furnished with the solid foundations required for work in research and development.